Section 1 Introduction. We're going to talk about language models, which have been instrumental in advancing various fields such as natural language processing, code generation, quantitative reasoning, and theorem proving. However, one of the main hurdles with these models is how to effectively incorporate a large amount of new information. The usual method of fine-tuning the model is not only resource-heavy and complicated to manage, but it also doesn't always provide a clear path to integrating new knowledge. For instance, if we fine-tune a model on a text like Alice in Wonderland, it doesn't necessarily equip the model to answer questions about the story. Instead, it trains the model to predict the next word or complete hidden sentences. An alternative approach is to integrate the new knowledge within the context, but this method is significantly limited by the model's ability to handle a large context length. In our research, we point out a major obstacle in increasing the context length. As the number of documents grows, the proportion of relevant to irrelevant information decreases. This often leads to overlaps between keys associated with irrelevant values and those linked to relevant ones, making it harder for the model to distinguish between them. We call this problem the distraction issue. To address this, we introduce the focus transformer, FOT, a novel technique specifically designed to tackle this issue. The FOT allows a subset of attention layers to access an external memory of key-value pairs using the k-nearest neighbors (KNN) algorithm, similar to the method used in previous studies. This mechanism effectively extends the total context length. What sets the focus transformer apart is its training procedure, which uses contrastive learning. This approach deals with the distraction issue and allows for larger memory capacities. During training, we intentionally expose the memory attention layers to both relevant and irrelevant keys. This encourages the model to differentiate keys associated with semantically diverse values, thereby improving their structure. We also introduce LongLLaMAs, which are fine-tuned OpenLLaMA models with FOT. These models show that our method doesn't require a long context during training and can be applied to existing models. Importantly, LongLLaMAs perform significantly better on tasks that require long context modeling. They can handle a context length of 256K on the passkey retrieval task. Our research contributions are as follows. 1. We identify the distraction issue as a major challenge and a key barrier to increasing the context length in transformer models, especially in multi-document scenarios. 2. We create the focus transformer, FOT, designed to mitigate the distraction issue. FOT includes a unique training objective that improves the key-value structure, enabling the use of large external memory and k-nearest neighbors lookup to scale the context length. 3. Our method is easy to implement and allows existing models to be enhanced with memory without changing their architecture. We demonstrate this on the 3B and 7B OpenLLaMA checkpoints. The resulting models, called LongLLaMAs, show improvements on tasks that benefit from increasing the number of few-shot demonstrations in the extended context. 4. We further examine FOT's capabilities across various datasets and model sizes. We show that a FOT trained with a total context of 512 tokens can extrapolate to 16 million tokens in a benchmark dictionary lookup task. We also evaluate FOT on long context language modeling tasks such as books, mathematics, code, and formal proofs, where it shows improvements in perplexity over baselines. Section Summary. Language models have been instrumental in advancing various fields, but effectively incorporating new knowledge remains a challenge. Fine-tuning is resource-intensive and doesn't clearly address knowledge integration, while integrating knowledge within the context is limited by context length. To overcome this, we propose the focus transformer, FOT, which allows attention layers to access an external memory through the k-nearest neighbors algorithm. By training the model with both relevant and irrelevant keys, we address the distraction issue and enable larger memory capacities, resulting in improved performance on tasks requiring long context modeling. Section 2 Related work. We've been studying various methods that have been developed to extend the context length of transformer models, which primarily focus on reducing the complexity of attention computation. For example, the Transformer XL model uses a method that stores previous context, allowing the context to be extended linearly with the number of layers. The Longformer model uses an attention mechanism that allows tokens to attend to distant tokens in a sparse manner, which reduces computational complexity. Other models like Big Bird, Long T5, and Hourglass also use sparse attention to manage long sequences. The Hourglass model reduces computation by downsampling activations in intermediate layers, enabling longer contexts. The Colt5 model proposes conditional computation to save memory and allow for larger contexts. The memorizing transformer model uses a method similar to a k-nearest neighbors lookup to select the most relevant tokens, which can also be seen as a way to reduce the computational complexity of attention. Our work aligns with these approaches, and we aim to train a key space that can handle longer attention context lengths, thereby improving long context capabilities. Previous works such as retrofitting, and memorizing transformer have shown a promising direction for fine-tuning existing language models to add new capabilities without needing to retrain the entire model. More recently, several works have explored fine-tuning the LLaMA model to extend its context length. The landmark attention method proposes a compression scheme of LLM's context into landmarks, which increases the context length of LLaMA 7B to 32K. The position interpolation method introduces a modification to the rotary positional encoding scheme that enables fine-tuning for a 32K context. Unlike these methods, our approach does not depend on positional encodings. By removing positional encoding in memory, we can extrapolate to 256K tokens, even though the model was only trained on sequences up to 8K. This allows for a theoretically unlimited context length. Section summary. Various approaches have been developed to increase the context length of transformers, such as caching previous context, employing sparse attention, downsampling activations, and using conditional computation. Previous works have also explored fine-tuning language models, LLMs, to extend their context length, either through compression schemes or modifications to positional encoding. In contrast, our method does not rely on positional encodings and allows for extrapolation to theoretically unbounded context length. Section. Contrastive learning. The concept of contrastive learning. Contrastive learning is a method that aims to improve the quality of representations by comparing positive and negative examples. Two well-known methods that use this approach are CLIP and SIM-CLR, which have shown excellent results in the field of image processing. During the pre-training phase of contrastive learning, negative examples are kept in the same batch to learn how to differentiate them from positive examples. It has been shown that increasing the batch size in contrastive learning can improve the quality of representations. However, it has been observed that the embedding space in language modeling can suffer from degeneracy, where embeddings are tightly packed into a narrow cone, making it difficult to distinguish between them. To address this, TRIME proposes a training approach that uses memory augmentation and in-batch negatives to improve the quality of representations. Our approach differs from this in that we incorporate negatives into the memory attention layer rather than interpolating them in the output layer. Introducing the focus transformer. Our method, the focus transformer, FOT, is a simple extension of transformer models that can be used to train new models or fine-tune existing ones, even large ones, with a longer context. FOT uses memory attention layers and a crossbatch training procedure. Memory attention layers allow the model to retrieve information from an external memory during inference, effectively extending the context. The crossbatch training procedure encourages the model to learn key value representations that are easy for a memory attention layer to use. Memory attention layers. Memory attention layers are equipped with access to an external memory database during inference. Specifically, each query in these layers attends to preceding keys from the local context and the top k most matching keys from memory. The memory keys are ranked based on their inner product with the query and retrieved using the k nearest neighbors (KNN) search algorithm. We use the exact KNN search implemented in FAISS. The memory is gradually filled with key value pairs processed beforehand. Our memory attention layer design is closely related to previous work, but we have replaced the gating with a simpler mechanism, which has proven to be more effective in our applications. We have removed positional encodings in memory layers in all our models except LongLLaMAs, allowing LongLLaMA checkpoints to be a drop-in replacement for LLaMA checkpoints. Section summary. Contrastive learning is a method that compares positive and negative examples to learn good representations. The focus transformer, FOT, is an extension of transformer models that uses memory attention layers and crossbatch training to improve the model's ability to retrieve information from external memory at inference time. The memory attention layers attend to preceding keys from the local context and the top k most matching keys from memory, which are ranked by inner product with the query. Section 3.2 Crossbatch Training Procedure. We've developed a unique training method to enhance the structure of the key value space in transformer-based models. Our goal is to shape this space in a way that allows a memory attention layer, which we'll call L, to easily focus on relevant information. Our approach is inspired by contrastive learning. We expose L to key value pairs from the current and previous local context of a given document, which we refer to as positives, and from unrelated documents, which we call negatives. We do this in a way that allows for differentiation. To achieve this, we use a data pipeline where each batch element corresponds to a different document. We embed the previous and current local context for each document processed. For each document in the current context, we create a set of key value pairs from the previous local context of the document, positives, along with pairs from other contexts, negatives. We also experiment with varying the number of previous contexts and negatives for different batch elements. We don't use external memory during training, which has two significant implications. First, the operation is fully differentiable, allowing us to improve all the key-value pairs. Second, the procedure is easy to implement. It doesn't require any additional loss and is done at the data loading pipeline level with a minor self-attention change. The only new hyperparameter is D, which determines the ratio of positive to negative samples. We usually find it beneficial to start with small d values, less than or equal to 8, and later switch to larger values, greater than or equal to 64. We also discuss what we call the distraction issue. We believe this is a key problem when using large memory databases. During standard training, the model isn't encouraged to distinguish keys from different documents. We find that the attention is evenly spread on related and unrelated documents. For a document, let's define the positive attention mass as the sum of the softmax weights related to the document divided by the total sum of the softmax weights. We observe that this ratio is approximately equal to 1d, suggesting that the attention is equally distracted by the positive and negative keys. This is undesirable because as the memory scales, the attention becomes increasingly distracted. However, our Crossbatch method largely mitigates this distraction issue, resulting in more focused attention. We also show that the distraction issue negatively impacts metrics like perplexity. Section summary. The authors propose a novel training procedure for transformer-based architectures to improve the structure of the key-value space, allowing for easier focus on relevant information. They achieve this by exposing the memory attention layer to key-value pairs from the current and previous local context of a document, positives, and unrelated documents, negatives, in a differentiable way. The authors also identify the distraction issue, where attention is evenly spread on related and unrelated documents, and show that their Crossbatch training procedure alleviates this issue, resulting in a more focused attention. Section 4 LongLLaMA, extending LLaMA's context length with FOT. In this section, we're going to discuss how we've expanded the context length of the LLaMA model using FOT, a method we're calling LongLLaMA. We found that FOT can be used to fine-tune existing large models, allowing them to handle longer context lengths. We started with the OpenLLaMA 3B and OpenLLaMA 7B models, which were initially trained with 1 trillion tokens, and fine-tuned them using FOT. The resulting models, which we've named LongLLaMAs, can handle context lengths far beyond their original training, even up to 256,000 tokens, while still performing well on tasks with shorter contexts. We've made the code for these models available on GitHub, and the LongLLaMA 3B model can be found on Hugging Face. It's important to note that our models are backward compatible, meaning they can be used with any existing LLaMA code, although they won't have the extended context capabilities when used in this way. In terms of the experimental setup, the architecture of the LongLLaMAs is the same as the original OpenLLaMAs. For the 3B LongLLaMA model, we used 6, 12, and 18 as the memory layers, and for the 7B model, we used 8, 16, and 24. We fine-tuned these models on 10 billion and 3 billion tokens respectively, using FOT, a context length of 8,000, and a dataset mixture based on Red Pajama. There are a few minor differences from the standard FOT procedure. First, we kept the positional encodings in the local context of the memory layers. This isn't necessary for FOT, but it ensures our models are fully compatible with any existing LLaMA code. Specifically, queries and keys from the local context, up to 2,000 tokens, receive the standard LLaMA rotary positional encoding, while memory keys are encoded as if they were in position 0 in the local context window. Second, we used dense attention instead of KNN retrieval, as we found the performance differences to be minimal and dense attention is simpler to implement. Lastly, we adjusted the Crossbatch training procedure to give us more control over the number of additional contexts and the ratio of positive to negative samples. You can find more details about these differences in the appendix. Section summary. In this section, the authors demonstrate that their fine-tuning of transformers, FOT, method can be used to extend the context length of existing large models. They fine-tune OpenLLaMA 3B and OpenLLaMA 7B models with FOT, resulting in LongLLaMAs that can extrapolate beyond their training context length, up to 256K, while maintaining performance on short context tasks. The authors provide the experimental setup and note some minor differences in their approach compared to standard FOT procedures. Section 4.2 Context Length Extrapolation on the passkey retrieval task. We first examined the effective context length of our model, LongLLaMA, which refers to the distance over which tokens can effectively interact with each other. We used a synthetic task called passkey retrieval to measure this. In this task, the model must locate a passkey that has been randomly placed within a lengthy prompt. Our findings, as shown in the accompanying figure, reveal that our 3 billion parameter model can solve this task well beyond its training context length of 8,000 tokens, achieving an accuracy of 94.5% for prompts of 100,000 tokens in length and 73% for prompts of 256,000 tokens in length. Next, we evaluated the long context capabilities of these models on two tasks, TREC question classification and WebQS question answering. We used a few-shot learning approach, providing the models with as many demonstration examples as possible within the given context length. We didn't use structured prompting, but instead provided all demonstrations within the context. We found that longer contexts significantly improved accuracy on the TREC task and slightly improved accuracy on the WebQS task. The TREC dataset consists of 50 classes, and the model's task is to predict the class label based on in-context examples. Only 100 examples can fit within the standard context length of 2,000 tokens, so it's not uncommon for a given question to lack a class example, making the task impossible. However, increasing the context length and the number of examples reduces this risk. Additionally, having more demonstrations of the given class is likely to be beneficial. We then compared our few-shot optimization training (FOT) approach to standard long context fine-tuning. We found that FOT not only performs better for the context length used for fine-tuning, but it can also extrapolate beyond this context length, which the baseline model cannot do. For this comparison, we fine-tuned two models, one using FOT and the other, the baseline, using standard fine-tuning. Both models were 3 billion parameter models fine-tuned on 1 billion tokens using a context length of 4,000 tokens. We evaluated both models on several few-shot downstream tasks. In most cases, we found that accuracy improved when more few-shot demonstrations were provided in the extended context, from 2,000 tokens used by OpenLLaMA to 4,000 tokens used in our fine-tuning. On the TREC task, both models significantly benefited from the additional context, while on the WebQS task, the standard fine-tuning baseline did not show any improvement from the extended context. Notably, the model fine-tuned with FOT showed further accuracy gains when evaluated with context lengths beyond its training length, 6,000 and 8,000 tokens. This demonstrates the extrapolation capabilities of FOT, which are not present in the baseline model. Section Summary. In this section, the authors measure the effective context length of their model, LongLLaMA, by using a passkey retrieval task. They find that their model can effectively solve this task even beyond its training context length. Additionally, they compare their model to standard long context fine-tuning and show that their model achieves better performance and can extrapolate beyond the context length used for fine-tuning, which is not the case for the baseline model. Section 4.5 Performance on Short Context Tasks. We're going to discuss the performance of our models on tasks with shorter contexts. You might think that fine-tuning our models for longer contexts could negatively impact their performance on tasks with the original context length of 2000. However, we found that this isn't the case for our LongLLaMA models. We've tested them using the LLaMA evaluation harness library and found that their performance remains consistent across most tasks. You can find more details in the appendix and the table of average scores. This suggests that LongLLaMAs could replace LLaMA models, as they're compatible with the original LLaMA code. Next, we'll delve into an analysis of FOT. We've conducted a series of experiments on smaller models to further validate our approach. We're specifically looking to answer three questions. 1. How does FOT perform when we increase the context length at the time of inference? 2. Can we use FOT to extend the context length of a pre-existing, pre-trained model? 3. How well can it handle distractions, and how does this ability improve performance in tasks involving long context language modeling? We'll also provide an ablation study of our method and additional analysis. For the experiments in this section, we're using decoder-only transformer models with 12 layers and 184 million parameters. We've chosen 8 as the memory attention layer and tuned the number of top keys retrieved by KNN to 128. In most experiments, we start training with a small crossbatch dimension of 8 or less and switch to 64 or more after some training. You can find more details about the architecture and hyperparameters in the appendix. We're using two evaluation settings, single document and multi-document. The single document setting is typically used for models that process long contexts. In this setting, we clear the memory for each new document, ensuring that only the current document is available in the context. The multi-document setting retains memory across multiple documents without resets. This is similar to a long context retrieval task where the model must focus on tokens from useful documents without getting distracted by irrelevant ones. We're evaluating our models on the following long context language modeling datasets: PG19, English books, archive, mathematical papers, GitHub, code, and Isabelle, formal proofs. PG19 is a large dataset of English language books published before 1919, sourced from the Project Gutenberg archive. It's a well-established benchmark for evaluating long context language models. The archive dataset contains the LaTeX source of papers labeled as mathematics that we obtained by downloading articles through the archive bulk data access. The number of tokens per paper in this dataset is similar to that of a book in PG19. You can find details on the remaining datasets in the appendix. Section summary. The performance of LongLLaMA models on short context tasks remains intact, indicating that they can be used as a drop-in replacement for LLaMA models. Additionally, extensive experiments on smaller models validate the effectiveness of the FOD approach in scaling context length, extending pre-trained models, handling distractions, and improving performance in long context language modeling tasks. The evaluation is conducted on various datasets, including PG19, Archive, GitHub, and Isabelle. Section 5.2 Scaling of the context length to 16M. In this section, we're exploring how our method can handle a larger memory capacity to extend its context length. We use a simulated dictionary lookup task to test this. In this task, the model is given a set of key value pairs and then asked to identify the value linked to a specific key. We train our models using documents that are 512 words long. The first half of each document sets up the keys and their corresponding values, while the second half asks questions about the values linked to the keys defined in the first half. We use smaller models with 37 million parameters for this task. For our method, known as FOD, we use a local context of 256, meaning the model needs to use the memory attention layer to answer the questions correctly. We start with a dimension of 1 and increase it to 128 once the model can achieve a training accuracy of 98%. During the inference, we use 32 keys retrieved by the k-nearest neighbors algorithm. Our results show that after 5,000 training steps, FOD can effectively use a memory consisting of 16 million tokens and achieve an accuracy of over 92%. We compare this to a standard transformer model trained with a context length of 512. When we test different local context lengths, the results quickly deteriorate. We also look at fine-tuning FOD and extrapolating the context length. FOD is a minor modification to the standard transformer architecture, so it's possible to fine-tune existing models to give them a longer context length through the memory attention layer. We delve deeper into this analysis by studying improvements in perplexity on various datasets. We use a standard transformer model pre-trained for 100,000 steps with a context of 1,000 tokens as our base model and fine-tune it with the FOD objective. The data used for both fine-tuning and pre-training is the C4 dataset. The fine-tuning phase takes 10,000 steps. We use a crossbatch dimension of 128 and a local context of 1,000 tokens. We evaluate our models on 4 language modeling datasets that require a long context: Archive, PG19, GitHub, and Isabelle. We find that FOD consistently improves perplexity up to 64,000 tokens, even though it was only fine-tuned with a total differentiable context length of 2,000. We compare our model's perplexity to 2 baselines: the memorizing transformer fine-tuned with a local context of 1,000 and a memory size of 16,000, and the transformer XL fine-tuned with both a local context and window length of 1,000. All 3 models are fine-tuned from the same base checkpoint to ensure a fair comparison. When evaluated with a context of 2,000, our method performs as well as the transformer XL baseline, which has access to the previous context in all layers, unlike the memorizing transformer and FOD. Compared to the memorizing transformer baseline, we achieve better scaling when evaluated with a 64,000 context length and significantly better perplexity values. Our method doesn't require training on long sequences, which is reflected in the lower perplexities of FOD when evaluated in a zero-shot setting. Section summary. The authors conducted a synthetic dictionary lookup task to test if their model, trained with their method, can effectively utilize a large memory to extend its context length. They trained models using documents of length 512 and found that their FOD model, after 5K steps of training, can effectively utilize a memory consisting of 16M tokens with an accuracy above 92%. Additionally, They fine-tuned existing models using the FOT objective and observed steady perplexity gains up to 64K tokens, achieving results on par with the Transformer XL baseline. Section 5.4 Handling Distractions in Language Modeling Tasks. In this section, we're going to explore how managing distractions in a multi-document environment can improve language modeling. We'll use the PG19 dataset as our testing ground, and we'll be looking at how well our model can predict the next word, a task known as language modeling, as we change the size of our multi-document memory, which in this case is made up of books. You might think that the memory tokens related to the current book would be helpful, and our findings confirm this. However, tokens from other books are likely to be more of a distraction than a help. As we can see in the accompanying figure, the more we increase the crossbatch dimension d, the better our model becomes at predicting the next word. This finding is consistent with what we've observed in previous sections, suggesting that by reducing distractions, we can improve our language modeling. What's more, all versions of our FOT model are able to use memory to achieve much better word prediction than the standard transformer model, which doesn't use memory. As you might expect, the more memory we use, the more difficult word prediction becomes, but this increase in difficulty is gradual. In the standard version of FOT, word prediction difficulty only increases by 0.18 when we scale up to more than 500,000 tokens. It's also worth noting that the word prediction difficulty of FOT is close to that of the memorizing transformer with single document memory, which we consider a soft lower bound because it doesn't have to deal with distractions from unrelated books. The main reason we developed FOT was to improve performance in multi-document environments by reducing distractions. Interestingly, our method also helps to extend to longer contexts, even when tested in a single document setting. To investigate this, we fine-tuned FOT and tested its word prediction on the PG19 dataset with different context lengths in a zero-shot fashion. To deepen our analysis, we introduced an additional parameter W, which represents the number of previous contexts used in crossbatch training procedure. We tested W equals 1, the standard setting for FOT, which corresponds to a total differentiable context of 2 times 1024, and W equals 2, which corresponds to a total differentiable context of 3 times 1024. As we can see in the accompanying figure, our model improves as the context grows, even far beyond the training context length, which supports our hypothesis that FOT helps with extending to longer contexts. Furthermore, D equals 2 performs significantly better than D equals 1. When we compare D equals 1 and W equals 2 with D equals 2 and W equals 1, we find that the former performs slightly better, which makes sense because it has a longer training context. Section Summary. In this section, the authors investigate the impact of handling distractions in language modeling tasks using a multi-document setting. They find that by mitigating distractions and increasing the crossbatch dimension, they achieve better perplexity in language modeling. Additionally, their method of handling distractions also helps in extrapolating to longer contexts, even in the single document setting, resulting in improved performance. Section 5.6 Ablations and Design Choices. In this section, we'll delve into 2 crucial aspects of the crossbatch training process, its differentiability and the inclusion of negatives. We'll also discuss how it relates to the memorizing transformer in terms of training protocol and memory integration. For a more technical comparison between our method, FOT, and the memorizing transformer, please refer to the appendix. Firstly, let's discuss the impact of differentiable keys and values. We compared our method, FOT, with the memorizing transformer, which uses a non-differentiable memory of keys and values during training. In an experiment involving multiple documents, both methods were trained with a local context of 512. We found that FOT performed significantly better when the context was expanded during inference, confirming the benefits of differentiable keys and values. We also tested whether differentiable keys and values could enhance performance in a single document setting. Here, we compared FOT with a single negative, D equals 1, to the memorizing transformer with memory consisting of the previous local context. The results confirmed that differentiable keys and values can also improve performance in this scenario. Next, let's talk about the importance of negatives. We've found that negatives are crucial in a multi-document setting. In previous experiments, we noticed that increasing the number of negatives, i.e., increasing D, leads to more attention being paid to relevant tokens. We also found that without negatives in training, D equals 1, the model's perplexity significantly worsens as the context length increases. This confirms that both the use of negatives and differentiability are key for FOT to perform well. Now, let's discuss the relationship between our method and the memorizing transformer. The 2 main differences lie in the training protocol and how memory is integrated into the model. We've already discussed the benefits of crossbatch training, which includes using a contrast-inspired objective and backprop aggregating through the previous context. The memorizing transformer, on the other hand, has the potential advantage of being exposed to the entire memory during training. We conducted an experiment to further explore this, training the model for 499K steps using Crossbatch and then fine-tuning it with the memorizing transformer objective for 1K steps. Interestingly, we saw a significant improvement compared to the memorizing transformer training with the same step budget. We believe there's potential to further explore various training protocols that combine the best aspects of both methods. In terms of memory integration, FOT uses a simple approach where the key-value pairs retrieved by KNN lookup are treated the same way as the local context. The memorizing transformer, in contrast, uses a gating mechanism, a weighted average of the memory and local values. We found no performance difference between these two memory integration methods. However, we chose our approach because it doesn't require any architectural changes, making it easier to fine-tune existing models. We recommend using it. We speculate that the reason why gating isn't needed in FOT is another benefit of the fact that the crossbatch training backpropagates through the key-value pairs from the previous context, unlike the memorizing transformer, which can't backpropagate there and needs to rely on local context when computing gradients for keys and values. Another reason might be that the previous context is embedded for each batch, avoiding staleness. Section Summary. In this section, the authors discuss two important aspects of the crossbatch training procedure in the FOT model. Firstly, they compare FOT to the memorizing transformer and show that the use of differentiable keys and values during training is beneficial for FOT's performance. Secondly, they emphasize the importance of including negatives in the training process, as it improves attention allocation to relevant tokens in a multi-document setting. The authors also highlight the differences between FOT and memorizing transformer in terms of training protocol and memory integration, and recommend using FOT's memory integration approach due to its simplicity and compatibility with existing models. Section 6. Limitations and Future Work. Chapter 6. Limitations and Future Directions. Our study has paved the way for several potential areas of future exploration. We'll discuss these, along with the challenges and limitations we've encountered. Expanding memory capacity. This is a crucial area for future research. The main challenges here are largely technical. For instance, storing more than 16 million key value pairs would necessitate a multi-node system. In our tests, we used an exact k-nearest neighbors (KNN) search, which isn't scalable for large memory. Implementing an approximate KNN search would require significant engineering work and careful assessment of how the approximation affects the model's performance. Increasing crossbatch size, we found that a larger D value is beneficial. In our tests, we used D values of 64 or 128, which is the maximum that a single TPU-v3, TPU-v2 machine's memory can handle. In future research, we aim to increase D further and test on devices with larger memory or use multi-node training. Exploring contrastive learning. The FOT training method we used is based on basic contrastive learning techniques. This approach improved the key structure, helping to reduce distraction issues. We anticipate that other contrastive learning methods could also be beneficial. For example, hard negative mining could be used to leverage larger memory during training. We plan to explore this in future work. Integration with other methods. The development of long context methods is a vibrant area of research. We believe that some of these methods could be integrated with FOT, leading to mutually beneficial interactions. Section Summary. The limitations and future work of our research include scaling up memory to handle more than 16 key-value pairs, which would require a distributed multi-node system, and exploring the use of approximate KNN search to handle large memory. Additionally, we aim to increase the value of D and test on devices with bigger memory or utilize multi-node training for scaling up crossbatch. We also plan to explore other contrastive learning methods, such as hard negative mining, and investigate the combination of FOT with other long context methods for improved results.